Welcome to The Explainer. I am so glad you're here today because we are looking at something truly fascinating, classical control theory. Basically, we're going to see exactly how we take complex, seemingly abstract math and turn it into life-saving reality. If you're the kind of person who loves structured learning and you really want to understand the invisible forces keeping our modern, autonomous world from just, well, crashing down around us, you are absolutely in the right place.
Okay, picture this for a second. You've got a drone hovering high up on the sky, and suddenly, out of nowhere, it gets hit by a fierce, unpredictable, hurricane-force wind gust. Now, logically, it should just flip over and smash right into the ground, right? But it doesn't. And that brings us to the ultimate question we're answering today. Could a single mathematical function actually prevent that drone from crashing? Today, we are exploring exactly how invisible math prevents catastrophic physical disaster.
So let's kick things off with Section 1. Surviving a hurricane gust. Before we get into the heavy math, we really need to understand the intense, high-stakes environments where these control systems are absolutely vital. We aren't just talking about, a cheap toy helicopter hovering in your living room. We're talking about preventing mechanical failures in incredibly high-risk environments where human reflexes simply aren't fast enough. Think about autonomous drones delivering critical supplies right through the middle of a storm. Or, even more intensely, precision surgical robots operating inside a human body. Why does this matter? Because the math we are about to unpack is the literal difference between a smooth, perfectly controlled maneuver and a devastating crash or surgical error. And when you look at the practical applications for this, aerospace engineering, autonomous vehicles, advanced robotics, the big picture really comes into focus. If you're looking to build a career in literally any of these cutting-edge fields, mastering classical control theory is your cornerstone. It's the fundamental toolkit that makes all modern autonomous technology possible. Moving right along to Section 2, Anatomy of the Feedback Loop. Meet the real hero of our story. This is what actually fights back against that massive hurricane gust, the foundational feedback loop. It works in 3 steps. First, you have the set point. That's our target, where we actually want the drone to be. Second is the error. The system calculates the exact mathematical difference between where it is right now and where it should be. And finally, it takes that error and feeds it into the transfer function, which engineers call G of S. Think of the transfer function as the system's brain. It interprets the error and tells the motors exactly how hard to spin to fix it. Here's where it gets a little mind-bending. To actually design that transfer function, engineers have to completely shift how they view the world. On one hand, you have the time domain. This is chaotic. It's real-world seconds ticking by, sudden wind gusts, sensors rapidly firing, everything happening all at once in a messy, fast-paced blur. But to figure things out, engineers step out of that chaos and into the frequency domain. By smoothly and methodically analyzing how the system reacts to specific signal frequencies, we can calmly examine the system's core DNA. It lets us predict exactly how it's going to behave under stress without ever having to risk crashing a physical drone. Which brings us perfectly to Section 3, the Mathematical Stability Toolkit. Now that we're sitting comfortably in that calm frequency domain, we can start using specific mathematical weapons to conquer instability. Our first critical buffer zone is called the phase margin. Basically, phase margin is the amount of additional phase lag or delay in the system's reaction that our system can tolerate before it just becomes completely unstable. Think of it as your safety cushion for time. If your sensors lag slightly because they're processing a bit too much data, the phase margin tells you exactly how much of that delay you can handle before you lose control entirely.
Now, right alongside that is its counterpart, the gain margin. While phase margin is all about delay, gain margin is all about power. It tells us the amount of additional gain, or amplification, needed to hit the strict threshold of instability. It's a distinct numerical boundary for safe amplification. So, if a sudden gust requires the drone's motors to dramatically spike their power to compensate, the gain margin ensures that sudden burst of energy doesn't accidentally send the drone into wild, out-of-control oscillations.
And how do we actually calculate those boundaries? Well, let's walk through a worked example of the Routh-Hurwitz criteria for a 3-pole system. And hey, don't let the variables here intimidate you. It's actually pretty brilliant. By organizing the system's coefficients, those A, B, and C values, into these very specific rows corresponding to the powers of S, engineers can determine stability without having to solve massive, completely unwieldy equations. If all the values in that first column share the exact same sign, boom, congratulations, your system is mathematically stable. It's just a wonderfully elegant way to keep complex numbers totally organized and accessible.
Another absolute game changer in our toolkit is the root locus sketch. This allows us to visually track the poles of, say, a simple motorized arm. And it's crucial to understand these aren't just abstract dots drawn on a piece of paper. By tracking how these poles move as we tweak the system, we are literally mapping the physical movement of that robotic arm straight toward potential instability. Placing poles and zeros at the origin mathematically represents how the arm is going to physically drift or hold its solid position out in the real world.
All right, listen up, because I need everyone's full attention for this next point. This is a massive pitfall warning. I really want you to master this stuff, so I've got to give you this pro tip right now to help you avoid a critical error. Never, ever confuse your open loop gain with your closed loop stability. Seriously, it is such a common trap. Open loop is examining the raw components without the feedback. Closed loop is the actual functioning system checking its own errors. If you analyze your open loop gain and just assume that means your closed loop system is stable, your drone's going to crash. Period. Always double check which loop you are evaluating.
To see all of this executed perfectly, we have a fantastic real-world case study, Brian Douglas's drone control. Honestly, it plays out like a high-tech detective story. When a UAV is up in the air, its sensors are screaming conflicting information at it because of all the vibrations and wind. It's just pure chaos. But Douglas uses complementary filters and relies heavily on Bode plot analysis to separate the clues from the lies. The Bode plot lets engineers see exactly which frequencies are true signal and which are just noise. It effectively tracks down the absolute truth of the drone's position, keeping the UAV perfectly stable right in the middle of a storm. But to build those ingenious filters in the first place, engineers have to meticulously read through a MEMS gyroscope datasheet, and this requires incredible precision. You aren't just looking for the major numbers, you have to hunt down what's called the noise floor. That's the baseline level of static inherent in the tiny, microscopic sensor itself. If you don't mathematically identify and filter out that exact level of chaotic data, your feedback loop is going to aggressively try to correct for movements that aren't actually happening.
All right, moving into our final section, Section 4, Speed versus Smoothness.
So, we have our sensor data and our mathematical toolkit. Now we arrive at the ultimate dilemma, the one every single control engineer must inevitably face, the inescapable trade-off between speed and smoothness. On one side, you have speed, prioritizing incredibly fast reactions to sudden changes. On the other side, smoothness, prioritizing precise, perfectly jitter-free movements. The catch? You can rarely maximize both at the same time. A drone fighting a sudden hurricane gust needs aggressive speed to stay airborne, even if it jerks around a little bit to do it. But a surgical arm operating near a major artery? No way! It absolutely requires complete jitter-free smoothness. A sudden aggressive overcorrection in that environment would be an absolute disaster. This entire balancing act, mastering Bode plots, the Roth-Hurwitz criteria, tuning feedback loops to weigh speed against smoothness, it really is a pinnacle of classical mechanics. In fact, this exact mathematical application is heavily tested in advanced curriculums worldwide. It aligns perfectly with Cambridge A-level physics, Cambridge Further Math, and IB Physics HL. It is truly a foundational challenge for the brightest minds entering this field. Which brings us to our final thought. I want to leave you with this question to ponder. We talked about phase margin earlier, that safety buffer zone against delay. Now, in some systems, a 5-degree phase margin might be mathematically defined as stable. But is a phase margin of just 5 degrees truly safe for an autonomous surgical robot operating inside a human being? Think about that razor-thin safety margin. Think about the zero margin for error world of autonomous control, where pure mathematics is literally the only thing standing between life and death. I really hope this explainer helped you see the incredible invisible forces at work in the machines all around us. Keep analyzing the data, keep questioning those margins, and I will see you in the next explainer.